Felix and the committee for this very kind invitation. I'll connect myself, you can hear me better. Yeah, this is better. So thanks, Felix and the committee, for this great opportunity to speak to this society and to be back in Cambridge, where I spent many happy years. So it's nice to be back and to catch up. So this is a talk. I gave it this title from deep learning to the dark universe. It kind of brings together two things of great interest to me, but also to many other colleagues, namely the deep questions about the universe, what is made of, dark matter, dark energy, and so on, but also the need to use new tools to actually explore that. We can no longer just use the traditional approaches. So I thought, given it's people who come here from different branches of natural sciences, and even within physics, interested in different topics and so on, I thought I'll make this talk a bit more so interdisciplinary, rather than just a vanilla dark energy talk. I've given too many of those. Okay, so it's something different. And many of you have probably had already some lectures or even courses on machine learning, but I thought I'll just give an overview here, just in case some have not heard it. This is kind of using all kind of techniques which were used to be known as artificial intelligence and so on, to actually solve problems in astronomy. Now, the most common problems, and I'll give examples, are classification, right? To tell a star from a galaxy, to tell a spiral galaxy from an elliptical galaxy, to tell what's a supernova 1A, to identify arcs due to gravitational lensing. This is a bit more technical. Photometric redshift, something we've worked in quite a lot. This is a topic which I like a lot, but time is short, so I just listed it, and I have slides on it, but I'm not sure if we'll get to it. I am happy to explain a bit more about that, the methodological group, and also how to use those techniques to search for example, Planet 9. And of course, one cannot give today any talk on physics without mentioning gravitational waves. So as you can see, it's a mixed bag of topics, but that's exactly the idea, to show you that similar methods could actually help to resolve it. Now, we like usually to praise the human brain, right? I mean, the human brain is fantastic. That's how you do, you do all these, solve all these problems in your supervisions just with that machine. But let me show you a bit of limitation. So let me assure you, this plot, this diagram, is not actually an animation. And I don't know if it works, but can you actually all see all 12 dots at once?
No, I can't.
You can't. See, and that's, I think, they come and go. Is this how you see that?
Yeah.
They come and go. So it's not an animation, right? It's your brain playing tricks and just can't focus on more than a few points at a given time. I'm getting confused. It just comes and goes. For some reason, I saw those on the rows, but then the others disappear. Yeah, do you see the same? So it's really something we need a neuroscientist probably to tell us why this happens. But I like this illustration because it shows the limitation, right? We think, we can just look at images, we can look at plots, analyze it. So that's point number one. Is just even if you have only one system, and you stare at it all day, you still may not see all 12 points, right? Even with one system. Now, of course, the whole problem is becoming far more dramatic with the increase of data. I don't have to tell you that. 3.5 billion Google searches per day. It's probably changing. LHC, the Large Hadron Collider at CERN, there are 600 million collisions per second, although only 100% are 100 per second are interesting, right? So there's a lot of kind of needle in a haystack problem. Lots and lots of data. How do you decide what you throw away so that you're left just with the subset which is relevant for detecting the Higgs, for example? And then this is closer to my heart. These are surveys. So I can tell you, I haven't made a historical summary here, but I came to Cambridge from Israel to do my PhD in the Institute of Astronomy in 1985. Sorry, last century. And I actually worked on the distribution of galaxies, and the sample we had galaxies with redshifts only a few thousands, and those without redshifts only just the magnitudes and sizes. You know, I was very proud of my PhD. I used a sample after combining 3 samples of 30,000 galaxies. Okay, this was the big data of the time, and we made all kinds of interesting plots of the distributions and so on, and discovered the great attractor and all that. Now the Sloan Digital Sky Survey. My apologies for all these acronyms. We have a problem in this field. Too many acronyms. Sloan Digital Sky Survey. This is generated about. This is on a ground-based telescope. Fantastic data set. Some of you might have done projects using that. This has produced 200 gigabytes per night. Okay. Dark Energy Survey, in which I've been involved for nearly 15 years, is producing, of course, if it's not cloudy, is producing about 1 terabyte per night. And eventually it gives you a catalog of 12 million galaxies. LSST, which is a very ambitious telescope being built on a neighboring hill in Chile, that's where Dark Energy Survey is, LSST is also there. Here we're talking about an increased order of magnitude, 15 terabytes per night. In fact, it's also a very important time domain, so it will be like a movie of the universe. You actually be able to look at objects changing their light and so on. And this is going to lead to a catalog of about 1 billion galaxies. And Euclid, which is an ESA, European Space Agency. By the way, Euclid is not an acronym. It's actually truly named after the Greek geometer. That's less because it's in space, so the amount of data it can gather is a bit more limited. It's about 850 giga. Again, 1 billion galaxies. And SKA is an amazing radio. There's actually 2 sets of radio telescopes, one in Australia, one in South Africa, and the construction here we're getting to the 1 petabytes per day. Incidentally, those projects where I say 1 billion galaxies, they cost about $1 billion. So I like to say that, it's only, just each galaxy costs only $1. It's a very good bargain to the taxpayer. It's $1, you get a galaxy, not a galaxy. You can name it after yourself if you like. But also, one should not forget the effort of simulations, right? That huge simulations, and you can, for each real universe, you can, 10 times more, 100 times more, 1,000 times more simulations, especially if you're trying to model different universes. So I think there's no need to preach anymore to explain why it's important. Now, big data, what is big data? If you look at Wikipedia, it says data sets that are so large or complex that traditional data processing applications are inadequate to deal with. Of course, what's traditional, right? So what was cutting edge yesterday becomes traditional. We need something new. So it's a moving target. And there's all this jargon about the V's. They're all it's volume, velocity, variety. There are, by the way, another 3-4 words that begin with a V, which people use to describe it. So this is by one of the founders of this kind of big data enterprise. In reality, what we do, and I think you might have done it in your lab work, is you're trying to discover things in your data set, right? If you had only 10 objects, you look at it and maybe discover something. But, if you have millions and billions, It's just more difficult, so trying to characterize the known, to assign some new classification tags, and of course to discover the unknown. And of course, when you have large data set, you can talk more about the typical, but not less interesting is the rare. So it could be that you do a survey of billion galaxies. The one interesting one is D1, which is against every theory, and I don't know, turns out to be a problem for existing models. Now, a bit of terminology. It's all over now, right? Artificial intelligence, machine learning, deep learning. What's the connection between them? I try to illustrate it. Sorry, the letters are a bit small, but I'm sure you can follow me. So I think we are in a wider circle here of inference from big data, right? The word inference is very important. It's what do you infer from the data? And that's a big thing in many ways, and if you're in Cambridge, I'm sure you're familiar with Bayesian methods, and I'm sure some of your supervisors are, some of the world's leaders in that. There's unfortunately an eminent person called David McKay, who said he passed away, who was actually in the Cavendish laboratory, was a professor there, and published a very important book on inference methods, and many other people such as Steve Gall and others. So I'm throwing in some names. Some of them might be supervising you. But under that, I think there's this artificial intelligence, which was very popular in the 80s. The concept then went out of fashion, and now it's back again. And the government loves it. I'll tell you later about how much money is coming our way for this area. And I put in brackets some examples, for example, classifying galaxies. Then most people would say that machine learning is a subset of artificial intelligence, give or take. It's a matter of terminology. So here I'll show you examples about neural networks and so on, how to classify supernovae. And then deep learning is a subset of machine learning, which is another step which saves us from, as I explained in a moment, from doing a pre-processing of feature extraction. You let the data speak for itself. And I'll show examples on various problems along these lines. Okay, so it says, as I said, old history, of course, machine learning, artificial intelligence was not invented by astronomers. We shouldn't get the credit for that. It was invented by computer scientists. As the name implies, it was inspired by trying to understand the human brain, how the human brain operates. But then we humble astronomers kind of, over the years, kind of grabbed ideas and said, is it good for us? So in my youth, I was still in Cambridge then, you've all taken, I'm sure, a course in astronomy, so galaxies fall into different types. Broadly speaking, sparse and ellipticals, but there are many subtypes. You can put it on a scale of 15, based on an astronomer called the Voculaire. And back then, it didn't make any sense to me that people actually do it by eye. They look, there were these 6 or 7 gurus at the time who just look at an image and say, this is probably a galaxy. It didn't make sense. So I thought, is there something better? And indeed, we used this was in Science magazine. We used an artificial neural network. We sent galaxy images to the 7 living gurus at the time. One of them refused ideologically. He said it should all be done by eye. He never responded. Well, he sent a letter explaining why he's not participating. Others agreed. And first we showed the scattering among them. So on a scale which goes -5 to 10, the Voculaire system, T-type, the scale was about 2 units. And I did it with a PhD student at the time. Avi Naim still lives in Cambridge, by the way. And but then we showed that artificial neural network can actually replicate quite easily, which at the time was kind of new. Then colleagues, former student of mine, Chris Lintott, went on and set up Galaxy Zoo, the urban Galaxy Zoo, which is where he asked many members of the public to classify. But again, I'll have a slide later that we showed that this can be replicated. So that was the idea. This came, I think, was published in '95. This is a colleague from UCL who, not knowing about each other, He used it for tagging particles in accelerators. In fact, he and I, his name is Nikos Konstantidis, he and I are now co-directing a center for doctoral training in data-intensive science. If you're interested, this is a nice route for a PhD. So we kind of compared notes on that. But the here and now is that, while at the time I had a PhD student working for 6 months writing a code for neural net, now of course there's a lot of free software out there. This is something called scikit-learn. So you can just download it, whatever is taken people many months to write. There's all these packages. Lots of methods here. About half a dozen algorithms, such as neural networks and what's called a random forest is another method. Support vector machines. I don't have time to go through all this, but the concept is when you have supervised learning that you show a sample where you know the answer, you parameterize it. So I'm not writing equations, but you parameterize it, and the system learns from experience the free coefficients, for example, weights in the case of neural net are getting frozen, and then you show new objects, right? So that's the idea. It's not different from fitting a polynomial. So for those of you who have not heard at all, but it's like, data points, you fit a polynomial, that's your model. And then when new data come along, you can predict the unknown. So all we're doing here is, for example, galaxy types. You say type equals a function of 23 parameters. You fix those parameters based on knowledge like this human expert, and then you show it again. That's all it is. So I'm trying, if anything, to demystify. But there's a whole zoo out there, and you can do classification. You can look at the way objects are clustered in some hypercube. You can do regression, and you can do dimensionality reduction. And part of it is also a way of doing unsupervised learning. Okay, so it falls into supervised and unsupervised. Supervised when you know the answer, unsupervised data speak for themselves. And you can do, for example, a dimensional reduction, a PCA, principal component analysis, you might have seen your statistics course. Okay, so that's what it is. Now, there is, what's interesting, so I'm can do it in a descriptive way. It's late in the day. You had many lectures today. I started my day giving a lecture at 10 o'clock at UCL. So I'm just doing it in a more hand-wavy way. The concept here is for both the supervised and unsupervised, the traditional way has been to extract a certain number of parameters. Okay, so that's your input. So for a galaxy, although it's made maybe of 1,000 pixels, you can shrink it by, say, having 20 parameters. So you need a pipeline to do that and extract it and define the profile of the galaxy, the position in the center, the size, and so on and so forth. The good thing about it, you bring in some knowledge of the field, right? You know that the galaxy is something which has more light at the center than at the outskirts. You know it's roughly maybe not spherical, maybe elliptical. It's got some symmetry. So in some ways I like it because you put some knowledge, human knowledge into it. And I remember when I played with it some more than 20 years ago here in Cambridge, I had a naive question. I asked one of the local experts on this. I said, actually, why do I have to extract parameters? Why don't I just show the whole image? So this is it. That's the image. 1,000 pixels or 1,000,000 pixels, and let the machine figure it out. The answer I got, and this is from a very smart person, he said, don't be rude to the poor neural network. Still remember his words. Don't be rude. Why should you give to the neural network 1,000 pixels when you know that maybe 10 or 20 are sufficient? So 20 years have passed, and interesting enough, computer scientists came to us and say, actually, it's a good thing. Showed everything. We have big computers now. So why throwing away data? Just show everything. So this comes under the name deep learning. It's a nice buzzword. I'm not quite sure really what it means. So forgive me, it's in the title. But, some would say, I'm taking critical view here, not just saying it's great and do it. What the difference is that here, I hope you can see it, in the traditional pattern recognition, I first have feature extraction, okay? And I can do just that, okay? And based on that features, 20 points, I can plot the hypercube and say, this cloud has spirals, these are ellipticals, and so on. A more advanced version is the so-called, this is pattern recognition, okay? You can also do, this was the old days, again, feature extraction, and you can also do a trainable classifier, right? And this is a typical neural network. So I have my 20 parameters, and the answer is the type, and I train. It's just a fancy function with 3 parameters, which has nice derivatives, and you train and you find. However, the new thing is this deep learning, where you present the whole image, and you do it at different levels of features. I'll show another slide in a moment, but just to whet your appetite, what it does, because you don't throw away information, it performs much, much better. So this is a schematic diagram, and what it shows that if you have very little data, the traditional methods will do just as well. I mean, you don't need to go deep learning. But if your data gets bigger and bigger, the deep learning outperforms. Now, it's not so clear yet why. That obviously people look into it in computer science to justify it. Why does it do it? But just to explain, and some of you may know more than me about it if you've taken a course in machine learning. But the idea is you take a picture, in that case, a bird, and instead of I could have run some feature extractor which would only pick up that feature or the eye or maybe the tail and do just that and feed in 20 parameters about that bird. But instead of that, what we do, we actually convolve that image with filters. So you don't know about convolution, right? You take function F, function X, you convolve. So you convolve it with a filter, and you do different filters. Now you may ask which one would you choose. So there's no one answer to that. It's a bit ad hoc. But this way you capture everything. So there could be a filter which shows the gross feature of the bird. Could be another filter which maybe only shows the background. It's boring, but it's part of the image. And maybe your task is not to classify birds. Maybe your classify is to classify the background, right? Depends what you're asking. And then you do all these convolutions, and that's what you feed in. What's nice about use everything, what's not so great about it, I think it's lack of understanding. I mean, it's a bit of a black box. I don't know, maybe there are computer scientists in the audience who would contradict me. So that's why I have some reservation about deep learning. Is it deep understanding of something, or it's deep in the sense that you go in depth and extract all the information. Okay, so this is kind of if you like, the machine learning part of the story as understood by a humble astronomer. Now, when we come to the data, I mentioned already the square kilometer array, which is based in, being built. There's already a prototype working called Meerkat in South Africa, which seems to be working really well. It's a radio telescope, but it's really just, it's already, it's going to dwarf all the total internet. It's 5 times, say, the global internet traffic in 2015, okay? So everything we do with this, all over the world is just nothing. This is going to be much bigger than that. Incidentally, quite a big Cambridge involvement in this scale. But there are many other projects, and those of you who have taken a course in cosmology are familiar with the questions. What's the universe made of? What happened just after the Big Bang? The cosmic macro background. And many eminent people, the Cavendish and DMTP and the Institute of Astronomy. How did structure form? What is dark energy? What's dark matter? So I've been engaged in this research for many years, still back in Cambridge, where I was a PhD student, then a member of staff. and we did a survey called 2DF with only 250,000 galaxies. And when I was a PhD student, when I came early 80s, it was categorically announced that there is no cosmological concept, it's zero. And no dark energy, it was only cold dark matter, 95% of the universe and 5% baryons. And it was in the early 90s to work here, and then the supernova work, that there was a paradigm shift, and I'm glad to have witnessed paradigm shift, and I wish you to experience paradigm shift. And now, as you probably know, I did not even bother putting a slide because it's such a vanilla statement that only 5% of the universe is made of ordinary matter, 25% cold dark matter, and 70% dark energy. We still don't know what it is. So we devised all these experiments, and it's actually, there's even few more, but I've been, as you kindly mentioned, I was one of the co-founders of Dark Energy Survey. We hosted a meeting on Friday in London, actually, about that at the Royal Astronomical Society. There's now another one called DESI, which is spectroscopic. There's the SKA I mentioned. There's a precursor called LOFAR. Gaia measured billion stars in the galaxy. Again, there are some of the top researchers here in Cambridge. Planck satellites look at the cosmic macro background. Euclid is a satellite which will map the sky, galaxies and so on. And I mentioned LSST, which will give a movie of the universe. So a lot is going on, and you can see that the cynical remarks I said, when I said to people, let's use machines to classify, and people said, oh, for a few thousand objects, let's just get a student to do it. It's very cheap labor. Now it's clear with this billion, you just can't do it. You need to think differently. Okay. So in a few minutes, I'll just tell you the story of the survey in which I've been quite involved. This Dark Energy Survey, it's on a telescope in Chile. And the idea is to study dark energy using a range of methods, classes of galaxies, gravitational lensing, large destruction, supernovae. In January, we're going to finish all the observations. So that's it. But the analysis is still, it takes longer. So we have results from year 1 and a little bit from year 3 up to year 3. And I'll show some results about supernovae. So that's where we are, with over 200 papers already in the archive, and we don't have time to talk about the sociology of this field, but we follow the particle physicists working in large teams. So this is now 400 people in 7 countries. And I mentioned this is part of a much larger roadmap, and incidentally some of the work is done in our basement, so twice our team there, my colleague Peter Doyle and also David Brooks, constructed the big optical corrector, first for DES, then for DESI. It's a whole other story. So this is the picture, right? It's vanilla model. Well, now it's accepted, right? This is the paradigm shift, 5% ordinary, 25% dark matter, 7% dark energy. Dark matter, of course, gets diluted, the density gets diluted as the universe expands dark energy. If it's a constant, it's just that. But we don't know if dark energy, I didn't put Einstein's equation, we don't know if it's the left-hand side or right-hand side. And I think a brief summary is that it's a simple but pretty strange universe. Now, it is an inverse problem, right? We don't put a telescope and it says dark energy equals that, right? You have to infer it. And the first thing you do is with supernovae, you have the magnitudes against redshift, and from the so-called Hubble diagram, you can tell the properties of the universe, because it will be different universes. And this was the great breakthrough of the supernova teams, and won the Nobel Prize. You can use standard rulers, galaxies, C and B. You can also use gravitational lensing. So here is a telescope, there's a cluster, and a little circle, say a galaxy at a distance, would appear as having a banana shape because of the lensing, because of the bending. So you can imagine, and then you can make actually this contours of blue and red are actually, that's a picture of the dark matter inferred from that. So you do the inverse problem. You say, that's this distortion, what's in between me and the galaxy. So it may say that there's a big cluster there or not, and the circles are clusters. So these are the main probes of cosmology now. And you can imagine as more and more data, you'll have to develop new methods. So what's very common now is you heard about Bayes' theorem, right? You take your knowledge through chi-squared or likelihood, but you have to multiply it by a prior. That's what Bayes has told us. So you do an observation, you compress the data. This is the cosmic macro spikes. This is Bayes' theorem. The probability for the parameters giving the data and a particular model is some probability for the data given the model. That's like likelihood times the prior for the parameters, right? So Hubble constant cannot be negative. But we just had a debate writing a paper. Should you say the Hubble constant is larger than 20 km per second per megaparsec? Should you say it's larger than 50, right? So that's where priors come in. In any case, you do this based on inference machinery. You put the theory and that, and you get the answer. So this has been very much the big data approach. You can also do maps. This is a PhD student of mine, Niall Jeffrey, and here he used different techniques. For example, this is something called Wiener filter, which you might have seen in your studies, which is a bit kind of doesn't pick up peaks, okay? And this is something called Kaiser squares, after Nick Kaiser, who worked here as well for many years. And that's when you do a different trick called glimpse with some regularization. This is Lagrange multiplier for those who know this. And you can actually find the peaks, okay? This is an example of kind of advanced statistics. You may or may not call it artificial intelligence, but the idea is how do you actually recover the mass. Object classification, I think the concept is very, very simple. It's just to tell one from another, is this a cat or is it a dog, right? And I think I just already said quite a lot about it. This is an example of a neural network. We put some parameters like magnitudes and tell the type or the redshift. This is what's called a decision tree. What you do is on each parameter, which of these 20 parameters, you say if the length is less than that, it's that object. If it's above that, it's that object. And your free parameters are the cutoffs. So you minimize with respect to that. And, for example, a former student of mine, Mayan Shomaniak, what she did was to use these techniques to tell what's a star and what's a galaxy. Such a simple problem. What's a star, what's a galaxy? And the traditional methods, you could see, had some overlap between them, but with these neural networks, we could separate them very well. Okay. Now, this is only stars and galaxies, but you can imagine the medical applications deciding whether it's cancer or not. It's pretty important that you have this type of diagram and not that one, which is more ambiguous, and you may send the person to do an operation by not having to do it, right? So this kind of these questions on fidelity. I mentioned Galaxy Zoo. This was actually Chris Lintott was a PhD student. Sorry, he was an undergraduate at the Cavendish. Then he was a PhD student with us at UCL, and he's a professor in Oxford. So they went, well, without teasing them, I would say they went a step backward because they went to use humans to do the classification, right? 100,000 people, I think since then hundreds of thousands. But we have shown that you can actually replicate it quite easily so that's what I said before. You take the galaxy, you have parameters, and you classify it. So I told you the story about these experts, and we repeated with Galaxy Zoo, and I think the Galaxy Zoo are doing it, people are doing it as well. This was done with Manda Banerjee, who was my PhD student. Now she's a research fellow at the Institute of Astronomy. Some of you may know her. And you can get 97% success rate on elliptical stars and others. Photometric redshift, it's again, I'll do it quickly, although we spent many, many years on that. You have a spectrum of a galaxy, but if you can only measure its colors, only in broad bands, you can't tell the full spectrum. You just have those fluxes. And you can do the inverse problem. It's the same galaxy, just different redshifts, But you can see at redshift 0, it will have very little, there'll be actually a lot of flux there, yeah? But as it moves to 1.4, there'll be very little there. So you can do the inverse problem, right? You can say, based on the amount of flux, I can tell the redshift, and there have been many, many techniques to do that. Listed here, we won't go through it, but we devised neural networks methods, which work pretty well. And this is some examples of, the true redshift and the photometric redshift. Lots of scatter, but then you can percolate it into the analysis. And I'm taking you to the sort of, I'm pushing you to the deep end here, that when you do some cosmological analysis, you take, say, lots of weak lensing data, these distorted images, and you try to find a parameter called sigma 8, which is the amplitude of fluctuations and omega matter. And what's nice is these different photometric redshift methods give more or less some answer at the end of the day. So although for each galaxy we don't quite know, broadly they do a good job. So I wanted just to say that. Then come the more traditional things. I told you about this beautiful effect in nature. This is, by the way, a double cluster, but it's a cluster, and the distant galaxies get distorted. So these arcs, actually, they represent just one. It's just one galaxy, but because the light got bended, it turned into an arc. If it's exactly behind the cluster, you'll get actually a circle, and that's called Einstein ring. So the question is, here is a question, which one can also pose in medical imaging. For example, how do I find those arcs? Okay, how do I find them? So traditionally, people done by eye. So people are just looking. And by the way, in some using dark energy survey data, colleagues at the Fermilab wanted to do it by eye, and they gave the same images to members of staff and to undergraduates. And who found more arcs and who found them to be correct? The undergraduates, okay? Not the professors, okay? So that's all nice, but then the question is, when you are in the LSST era, should you do better and you want these techniques? So there's been data challenge, and we were not involved in that, but it's just to read that is this paper by Metcalf et al. They compare different methods, and the winner actually turned out to be these neural networks, these convolutional neural networks. Seem to have performed much better than humans and much better than just ordinary neural networks and so on. So you can read that. So that's a well-defined problem, right? It's all done on simulations and which produce arcs, and here there are arcs, here there are no arcs. This is, in the direction of an object where there's nothing that generates it. And this was given to experts visually and to all these artificial neural network methods in CNN. And with CNN, convolutional neural network, that was the picture I showed with the bird. They've done basically completeness, in other words, classifying correctly about 90% of the objects. So I think that's very encouraging. And with LSST, movie of the universe is 1 petabyte per night. There'll be 20 billion galaxies, but only 1 million. Okay, only 1 million of them. So it's a needle in a haystack problem. That's encouraging. Time domain. So you know that supernovae, these are exploding stars, but more precisely, it's a white dwarf that accretes mass, explodes. And so it's very difficult to see, but there's a rise and then fall. And nature has been very kind that these are standard candles, or they can be standardized to be standard candles. And that's how, when they were first measured by 2 teams, they seemed dimmer than expected. It turned out that the way to explain it is putting dark energy. It seems to solve the problem, and those 2 teams won the Nobel Prize, 2011, right? So it's a big business. And here we devised a project led by a postdoc called Michel Lochner, who is now back in South Africa. We devised a method of taking the data and use different techniques to parameterize it. So it's not deep learning yet. So here are 5 methods you can find on scikit-learn. A naive Bayes, which is pretty useless. KNN nearest neighbors. SVM support vector machine, and neural networks. And these are boosted decision trees, okay? So you have these decision trees, but you do something to boost the result so you get better performance. And it was all classified, and bottom line is that really this is a curve which tells you how well you get the true answer and how much you get the false. Ideally, you would like it to be very sharp, 0 to 1. So a perfect classifier will do just that. You can see that they all look a bit similar. Boosted decision trees in this problem seems to do best. So if, maybe next time you try machine learning, try that. First, naive Bayes is hopeless, but just for reference. So here is another example. Now, very soon from dark energy survey, we'll have thousands of those supernovae, so it's very suggestive to do that technique. And with LSST, we'll have millions, and this will be absolutely fantastic. Now, news from last week, dark energy survey. This is based on 200 supernovae from the dark energy survey, and which are the red ones, and another 100 or so from low redshift. Note the very thin scatter there, and this is again the Hubble diagram. The log of the magnitudes against redshift, and this line. This is the difference, right, between the data points and the models. And you can see this blue line, okay, so you've done it in the lab, right? You take data point minus the model. So you can see that the points sit very much on a straight line, which is the favorite model of about 0.32 omega meter, 0.68. You see, you can do it in a very detailed way. And I haven't told you what W is. It's ratio of pressure to density. If it's -1, it's Einstein's cosmological constant. So the important thing here, and I'm conscious of the time, is that really the so-called universe with cold dark matter, dark energy seems to be the winner, while this is the model I was told was the correct model when I was a PhD student, okay? My entire PhD as a PhD student of 3 years, 85 to 88, everyone told me this is the correct model, okay? So you can see things change. And this is in the parameter space, you can see that we have W. So I won't go to details, but if it's -1, it's just Einstein cosmological constant. Omega meter, what it is, these are the dark energy survey supernovae. This is the cosmic microwave background. They cross each other very nicely, and you get that peak. So I hope you get the idea. We need to classify many, many objects, and those techniques would be very powerful. Now, very quickly, as I said, one cannot give a lecture these days about anything without mentioning gravitational waves. They were discovered in 2015 by the LIGO team. Incidentally, there's going to be a talk tomorrow at the Institute of Astronomy at 4 o'clock by one of the LIGO people, Sheila Rowan. And so far 7 events, but should say the typo there, should we say 1 per month expected, and even later a few per week. So the amazing thing is there's 2 colliding black holes which produce that pattern. I'm sure you've heard about this. And it's very powerful, and you can do cosmology with it. You can tell us that the speed of gravitational waves is like the speed of light, because there's a flash of light that was emitted 1.7 seconds after the gravitational waves. You can also measure the Hubble constant and so on. I'll tell you just in a moment a personal story. So this was my night. It's a bit like, where were you when Jeff Kennedy was? Well, none of you were there, but where were you when the first gravitational wave hit the Earth? Right? Not was emitted, but it hit the Earth. And this was on in September 2015, I was actually at the telescope observing. This is the Dark Energy Survey. And we had an agreement with LIGO that if there is a signal, we can then change the program and look for an optical counterpart. So 4 o'clock, there was this phone call, and they said, we have a candidate for gravitational wave. Remember, up to this moment, none were discovered, right? They say that, and we also knew that occasionally they just do fake signals without telling you. So I thought, well, it's just probably a fake signal, it's not serious. In fact, the object they reported about was the one that is the first ever gravitational wave detected. In fact, it's that one, the one I just showed you, for which the founders of the survey got Nobel Prize, right? So it was that event, except at 4 o'clock they said change the observing program, look that direction. 8 o'clock, the Earth was shaking. So I've experienced an earthquake of 8.3 that night. I don't think there's a connection between gravitational waves and earthquakes. That's my knowledge. But maybe there could be a conspiracy theory there. So I'm sorry to report we could not observe that night. However, the telescope survived and my colleagues stayed on for another nights. Now they did not detect anything just because black hole does not actually emit optical radiation. But that's what it was like. Okay, so survivor's photo and all that. However, and again I'm speeding up, there were 7, it's difficult to see, 7 observed, and we're very lucky when the binary neutron star was reported. Then our project, Dark Energy Survey, was one of the half a dozen that actually observed the optical flash. Can you see that? This is the optical flash from the gravitational wave event, and it's actually inside a galaxy called NGC 4993, which is elliptical galaxies, and my student Antonella Palmasi and postdoc Will Hartley actually done some work on that galaxy. Now you can imagine, again, the talk is not about gravitational waves, but big data, but you can imagine somebody will be standing here in a few years, and rather than showing you 7, there will be this massive number of objects. And then again, it's finding a needle in a haystack to actually find. What they give you is a probability map. They don't tell you exactly where it came from. And now we have LIGO, 2 stations, and Virgo. It's a bit better. It's still tens of square degrees. So you don't know where it came from. So it's a major data analysis exercise to do that. Still on time domain, I'll also mention that this project, Dark Energy Survey, also was designed to do cosmology, but it has detected objects in the solar system. And this is one of them, this one. And 2 astronomers in California looked at those 6 orbits and said something must be wrong. Their orbits are too funny. They wobble. And they hypothesized planet 9. So remember, when I was a boy at school, we had 9 planets. Then Pluto got demoted. My 9-year-old daughter is very upset about it, by the way. But that Pluto got demoted, but it demoted, so we have only 8. But now there's this hypothetical planet 9. And we don't know. So I have a student, Ben Henges, who is actually searching for planet 9. So again, if you imagine what a task it is, you have to subtract images and you see some dots moving on the sky, and you have to figure out what is it. And Dark Energy Survey is a camera. It picks up everything. So it could be just an exploding star. Last the camera picked up the SpaceX is called, of Elon Musk. It picked up that object, right? So you have to do a very fancy analysis to say, is it SpaceX or is it Planet 9, right? So you can see the way it goes. So this actually brings me to the end. I only wanted to kind of tell you Is this okay? Like 2 minutes?
Yeah.
2 minutes? I'm nearly there already. That there's a lot of interest both ways. I mean, many of you presumably are trying to think about PhD, what to do for a PhD and so on. And we trained over the years many astronomers. I think I by now 30 PhD students over the years. And reality is there are no jobs in academia for everyone, right? I mean, it's much smaller. In fact, only 1 out of 10 will end up, for better or worse, in academia. What about the other 9? These are all bright people, and some of them actually prefer to do things which maybe could help humanity more than finding Planet 9 or dark energy, right? And I'm not being judgmental here. It's a matter of choice. So, if you like, there's a bottom-up interest in all this area of actually using these techniques. I showed some examples, but then use them in the real world for other problems, because instead of putting galaxy parameters, you can take parameters of a medical image which may or may not identify a cancer cell. So that's bottom up. Okay, individuals are interested in that. In fact, some astronomers even have some startup companies. But then there's also top down. The government really fell in love with artificial intelligence. They think this will solve all the problems of the world. I don't know if it's going to solve Brexit, but maybe. So there's actually money, while the money for research in astronomy is what's called flat cash. It's not changing. And, I'm sitting in various committees, and I don't see a change of that. Might even get worse with Brexit. But interesting enough, there's money coming from BES, or BES, that's the Department of Business and Innovation. Lots of money towards training people to do data science. This is called CDT, Center for Data Training, which appears also in other areas. But this is for data science, and we were the first to be awarded that center, and there are 7 others now in the country, including here in Cambridge. Okay, and that's great. We hosted actually in the summer. We hosted the summer school of the 120 or so PhD students from all over the country. We had it at UCL with a nice. There was a boat cruise, a conference dinner on River Thames. We have first year we had 16, and now we have another 10. So it's certainly what's interesting about this program, which is fully funded by the government, research councils, and also by some of those companies. And you can see some transfer for London, BBC, Met Office, but and others. What's interesting about it, the students would do a PhD over 4 years, but 6 months they would actually spend at the company, working on something completely different. They also have shorter projects with companies, so I supervised one with the Economist magazine, which had to do with producing a AI model, through AI, a model for the number of hits on their website. Okay? And there is a peak whenever Donald Trump makes some funny remarks, you see a peak. So you need a fancy algorithm to find all those peaks. So I think it's a very interesting time. This is from a book by a cosmologist, a book called Life 3.0. So while the first Life 1.0 was simple biology, which meant just could it survive and replicate? Yes. But can it design its software? No. Can it design its hardware? No. Then came Life 2, that's where we are. Cultural revolution. And yes, we can of course survive and replicate. You can also do software, but we still don't know. We don't have something that designs its own hardware. And then will come this phase, he thinks, which is technological, where we'll have, something which replicates, something that can design its software, and eventually build its own hardware, right? So I bet that your physics society, eventually, you won't invite someone from UCL, there will be a robot here giving the talk, right? Very likely. It saves, you don't even have to feed them. It's just a robot. But these robots will start designing their own robots, right? And then you can easily see quite a challenging and scary situation of where it's leading. But really, all these algorithms I described, which are well known in computer science, I showed you nice examples in astronomy. It's becoming very trendy to use them. Who knows where it's going to take us? I think it's a whole revolution. So, the summary, I think science is going some industrial revolution here, in analogy with the revolution at the time. A lot to understand in terms of spatial and time domains, a great training for PhDs beyond academia. Now, this I ask myself, I don't like selling big data and AI. Will it actually produce better knowledge? Okay, could general relativity, could it be discovered just by a neural network? Okay, I think there's still room there for the great minds and to think about it. Well, but I think my answer is it depends partially on nature. Okay, so maybe if nature is very complex and it's not been captured by a model, maybe this would help. In any case, and that's an example I didn't have time to show, you can put your model, you can put general relativity, but maybe use these techniques to look for deviations. Is there something beyond that? I think that's the way to go. But I think it's already past 9 o'clock. Thanks for listening.